This is a tutorial for using the R package scDECO to analyze instances of dynamic correlation. Dynamic correlation refers to the phenomenon when two random variables have their correlation dependent on some covariate or covariates. So you can see dynamic correlation in this plot because the correlation between x1 and x2 when x3 is small is a negative correlation, and as x3 gets larger and larger, the correlation between x1 and x2 grows into a large positive value. In scDECO, there are two main models that one can use to analyze dynamic correlation. The first is a bivariate Copula model, and the second is a bivariate Poisson-Gamma model. And they both have their own use cases that we'll get into a little bit as we demonstrate in R. So let's go ahead and jump into R and download the package. We download it from GitHub. And there is a requirement to have RJAGs because Poisson-Gamma uses RJAGs in its model fitting. So you might have to download JAGs onto your machine before you proceed. So we've downloaded it. Let's take a look at the Copula function, the scDECO.cop, the bivariate Copula fitting. The first argument is a two-column matrix where the first column is that random variable 1 and the second column is random variable 2. The next argument, x, this is a matrix of covariates, and these are the covariates that we think are impacting the correlation between the two components of y. And this x also in the model is a covariate for the mean of marginal y1 and marginal y2. So next, marginals, this is where we specify what marginals do we want to put into the bivariate Gaussian copula. Do we want a negative binomial, a gamma, etc.? W, that's another matrix of covariates, but instead of impacting the correlation in the mean like X did, this matrix of covariates is for the impacting the zero inflation. So we might say as W grows large, the zero inflation in the marginal grows large. The next arguments have to do with how many MCMC chains you want to run, how many you want to burn, and how many you want to thin. So let's go ahead and simulate data from the model. First, we simulate the covariates, X and W. We're just going to do uniform for demonstration's sake. Next, we want to specify the parameters which are determining in what way is the zero inflation dependent on covariates, in what way is the mean dependent on covariates, and in which way is the correlation dependent on covariates. These etas, this is specifying how the zero inflation in the respective marginals depends on covariates, covariate W precisely. The betas are how the mean of each marginal depends on covariates, and the tau is how is the correlation dependent on covariates. So we're going to simulate under this situation. And let's take a look at what data that got us. So we see it got us data where when X is small, the covariate X is small, we have not too much correlation going on, or perhaps even a negative correlation. And as X, the covariate grows larger and larger, the correlation becomes strong positive between our two marginals. We can look at what the exact functions are that we simulated from, the functions that relate covariates to parameters. So this function, this is showing how the covariate W is related to the amount of zero inflation in the respective marginal. We see when W is small, we have basically zero inflation, and when W is large, we get up to 25%. These two down here, this is showing how the covariate X impacts the mean. It shows when X is small, the mean is not so large, and then mean grows larger and larger as a function of X. And we saw that in the previous plot as well. Similarly for rho, when X is small, we have a large negative rho, or a large negative correlation. And then when X is large, we have a large positive correlation. So let's go ahead and fit the model. We only put 500 iterations here for time's sake, just so it'll go quicker. But if you were doing this in practice, you might want to put something more like 5,000 and some more burn. So notice we specified two zero-inflated negative binomial marginals. The other options would be beta or gamma, and zero-inflated beta, zero-inflated gamma. So those are the three distributions we have, and their zero-inflated counterparts. Now this should almost be done running, and then we can take a look at how good of a job it did in estimating our parameters. All right. So looking here at the estimated value compared to the true value, it looks like the function did a pretty good job, especially considering we didn't have too many Monte Carlo iterations. Let's see how the estimated functions compare. And it did turn out to be a good fit, so we were able to capture the parameters that generated the data. Now let's move on to the Poisson-Gamma version, the bivariate Poisson-Gamma model. So there are a few critical differences between this and the previous Copula model we just discussed. One main difference is that in this PG, scDECO.pg, the marginals are not free to be gamma or beta. They are defined to be negative binomial, zero inflated negative binomial. So that's a restriction that this model has. Another difference is that zero inflation, this B1 and B0 and B1, these refer to the zero inflation parameters. And those, instead of being a function of covariate W, these are a function of the marginal mean. So you specify if you think that zero inflation in your marginal will grow if you have a big marginal mean, or it'll shrink. That's what you specify with these parameters. And the last main difference is that the covariate, so before it was X and W, and we were able to feed them as any values, and they were treated just as known covariates. In this case, the covariate X3 is actually part of the model. It's modeled as being a zero inflated negative binomial, just like our two marginals, and we need to estimate its mean parameter and its over-dispersion parameter. So that's a critical difference with this PG. But other than that, we still have the same kind of Monte Carlo parameters here, and we can move on to simulating data from this model. All right, we simulated, so we have to specify the over-dispersion parameter for the two marginals, the over-dispersion parameter for the covariate, mean for the two marginals, mean for the covariate, and the tau, which is the same as in the previous model. This is how X3 is impacting the correlation between X1 and X2, or Y1 and Y2, those two marginals. Let's take a look at how this data turned out. And once again, we see the phenomenon of correlation growing as a function of covariate X, or X3 in this case. Also, we see a lot of zeros. This is typical of negative binomial data and zero inflated negative binomial data. And let's see what it looks like functionally to compare to the scDECO.cop. So a critical difference here is that our mu is not modeled as a function of covariates, it's just constant. Each mu is just considered as constant with respect to the covariate. But rho, once again, we see how it depends on covariates. It's a large negative correlation when covariate X is small, and a large positive correlation when X is large. So this one takes a while to fit, so I'm not going to do it in this video, but I fit it previously, and we can extract the results. So let's see how it did. We see that a pretty good fit was had for all parameters. And let's take a look at it if the functions match up. And indeed, we did very well, especially for rho, and we were able to capture the true parameter values that the data was generated from.